Well, welcome to our first flipped classroom video. This one is on understanding the atom and the subatomic particles that make it up. We'll also talk about isotopes and talk about ions. And by the end, I hope you'll have a mental picture for the atom, one that describes the location and characteristics of electrons, protons, and neutrons. So chemistry really is all about atoms. For us, atoms are kind of indivisible because they really don't change during chemical reactions. But it's important to know that atoms really are built of smaller particles. And we can ask the following questions about our system. So what are the parts of an atom? How do we build them together, or how are they arranged? In other words, what is the anatomy? Of those parts, how do they behave? What are their attributes? And lastly, how can one element be distinguished from another? What makes them distinct? So here's a schematic showing a highly stylized view of an atom, and it shows the principal players. Inside the nucleus, the center of the atom, we find protons, which are positively charged and indicated by little pluses here, and neutrons. And at some distance away, we find the electrons. So these are the core pieces. We have neutrons and protons residing in the nucleus, and then at some distance away, electrons. These are not really drawn to scale, as we'll indicate in the next screen. So we want to learn not just where they live and what they are, but what they're like. So atoms are indeed made of smaller pieces, as we said, electrons, protons, and neutrons, and we can describe them in symbolic form. Importantly here, the symbols E, P, and N are accompanied by a charge designation, a -1, a +1, or a 0 for zero charge, to indicate the charge value of each of these subatomic particles. So electrons are negatively charged bits of matter, protons are positively charged, and neutrons have no charge at all. And over here we can look at the absolute mass on a kilogram scale of these particles. You'll note that both protons and neutrons are virtually the same mass, whereas electrons, and this is a negative, that's important to know, are about 4 orders of magnitude times lighter than protons or neutrons. So all of these particles are tremendously light, but electrons are about 1/2000th the weight, or the mass, of the protons and the neutrons. It's also interesting to note that neutrons and protons are just about the same mass, but not exactly the same. And in your summer assignment, you no doubt learned why. Because neutrons really are protons and electrons kind of glued together to create a neutral particle. So, going back to that opening schematic, protons are positively charged, and they're just about the same mass as neutrons, which are electrically neutral. These two types of particles make up the nucleus, and at some distance away, the negatively charged electrons, which are considerably lighter than these nuclear particles, are orbiting the nucleus. So what makes an atom unique? We'll move on to that question. Well, first of all of the elements, well, those are unique types of atoms. So every element is a unique combination of subatomic particles that makes it its own type of atom. So here's a schematic showing a carbon atom with its neutrons and protons and electrons scattered about the outside, a magnesium atom, and a calcium atom. And what you can see here is, in this example, all of the nuclear particles and the electron count, they all are the same. But what is it that makes calcium calcium and not magnesium, or carbon carbon? Well, another way of describing elements is in symbolic form. This is the symbol for sodium. And we can use numbers to help us figure things out. And so you see that this is sodium 23, and this is sodium 24, and this is what we call the mass number. This is the sum of the proton and neutron count for that particular atom. But what makes both of these sodium is the bottom number, number 11, called the atomic number, or the number of protons. So what makes carbon carbon? Well, it's not these numbers here, it's this one, that describes the number of protons. All carbon atoms have 6 protons. Any more or any less, and it would no longer be carbon. And the same can be said for magnesium. It's the 12 protons that make it magnesium, the 20 protons that make it calcium. So, to review, an atom is defined by its proton count. Each proton count represents a unique atom. We call those elements. But you might be wondering, what's an isotope? And so on the last screen, we saw isotopes. We'll look at them again. Isotopes are versions of elements that have a unique neutron count. In other words, they differ by mass number, not because the proton count is different, but because the neutron count is different. So these were labeled as 2 isotopes of the element sodium. They both have 11 protons, that's what makes it sodium, but they differ in the mass number. And as we break this down a little bit and look over here, we can see why the mass numbers are different. It's not because the proton counts are different, it's because isotope 2, sodium-24, has 1 more neutron than does its buddy over here, sodium-23. So in every other respect, they're exactly the same. They have the same electron count and proton count. They're both electrically neutral. This one, isotope 2, is just a little heavier, and that's because it has 1 more particle in the nucleus, 1 more neutron. So an isotope is a version of an element with a unique neutron count, or we might say a novel mass number. These are both sodium because they both have 11 protons. It's the difference in mass number that makes them 2 distinct isotopes. And we were talking about electrons and protons being balanced within an atom so that there's no charge, but suppose they're not balanced. Suppose those tiny charges on electrons and protons fail to cancel each other out. Well, that's when you have an ion. So here's an image that shows a sodium atom and a chlorine atom, I would say, instead of chloride. And what's happening here is we can see an electron outside here, some distance from the nucleus, is about to be transferred from sodium to chlorine to make it chloride. So here, electrically neutral, the same number of red dots on the outside representing electrons as protons on the inside. The same thing is true for chlorine over here. But when we switch to the other side, this is now a positive sodium atom, a cation, a positive ion. And that's because we've wiped away one of those negative charges, leaving 11 protons, but now only 10 electrons. 1 more proton than electron, a positive 1 ion. Meanwhile, chlorine turned into chloride by accepting an electron, and if we count all of these, I think we're going to find 18 electrons, but only 17 protons. So 1 more electron than proton, that would leave the atom negatively charged. That's an anion. So an ion is an atom that's unbalanced. Their charges fail to add up to 0. Now it's important here that we care both about the sign, positive or negative, and the magnitude. How many extra positives, how many extra negatives. So both of those are very important in chemistry as we count up the pieces and figure out the charges of our atoms.